Hello friends, and welcome back. In this video, we will learn how a compact 220V AC SMPS mobile charger can be built using the TNY267 integrated circuit. Although the circuit looks simple, it contains all the important sections required for converting dangerous high-voltage AC mains into a safe low-voltage DC output suitable for charging a mobile phone. Let us understand the operation stage by stage. On the left side of the circuit we can see the AC mains input. The charger is designed to work from a wide input range of 100 volts to 240 volts AC at 50 or 60 Hz. This allows the charger to operate in different countries without requiring any voltage selector switch. The lower AC line first passes through a 10 ohm, 1 watt resistor and a 1N4007 diode. The 10 ohm resistor acts as an inrush current limiter. When power is first switched on, the capacitor initially behaves like a short circuit. The resistor helps reduce the sudden charging current and protects the components. The 1N4007 diode provides half-wave rectification and also offers protection against reverse voltage conditions. Next we have a 10 microfarad, 400-volt electrolytic capacitor. This capacitor charges from the AC mains and stores energy. The capacitor smooths the rectified AC and creates a high-voltage DC supply. When the charger is connected to a 220-volt AC main source, the capacitor typically charges up to approximately 220 times 1.414 is equal to 311 volts DC. Therefore, this capacitor provides around 310 volts DC to the primary side of the SMPS. This high-voltage DC becomes the main energy source for the switching converter. The heart of the charger is the TNY267 integrated circuit. The TNY267 belongs to the tiny switch family from Power Integrations. Inside this small IC there is a high-voltage MOSFET, oscillator, current limiter, thermal protection circuitry, and control circuitry. Because all these functions are integrated into a single package, only a few external components are required. The TNY267 rapidly switches the transformer primary winding on and off at a high frequency, typically around 132 kHz. This high-frequency switching allows the transformer to be extremely small compared to traditional 50 Hz transformers. The transformer primary winding consists of approximately 140 turns. One end of the winding is connected to the positive high-voltage DC rail. The other end is connected to the drain pin of the TNY267. When the MOSFET inside the TNY267 switches on, current begins flowing through the primary winding. As current increases, magnetic energy is stored inside the transformer core. When the MOSFET switches off, this stored magnetic energy collapses and gets transferred to the secondary winding. This process repeats thousands of times every second. Across the primary winding we can see a BA159 diode and a 180-volt transl or Zener diode. This network protects the MOSFET inside the TNY267. Whenever the transformer releases its stored energy, high-voltage spikes can be generated. If these spikes are not controlled, they may damage the switching MOSFET. The BA159 and 180-volt transl clamp these spikes to a safe level and absorb excess energy. This greatly improves reliability and increases the life of the charger. The transformer secondary winding has approximately 8 turns. Because of the turns ratio between the primary and secondary windings, the high voltage is stepped down to a much lower voltage. The transformer also provides complete electrical isolation between the dangerous AC mains and the mobile phone output. This isolation is one of the most important safety features in any SMPS charger. Even though the primary side operates at around 310 volts DC, the secondary side remains electrically isolated from the mains. The secondary voltage appears as high-frequency AC pulses. These pulses cannot directly charge a phone. Therefore, a BA159 fast recovery diode is used as the output rectifier. The diode converts the high-frequency AC pulses into pulsating DC. Because the switching frequency is very high, a fast diode is required for efficient operation. After rectification, a 220 microfarad, 35-volt capacitor filters the pulsating DC. The capacitor stores charge and smooths the waveform. As a result, the output becomes a stable DC voltage suitable for powering electronic devices. This filtered DC voltage is supplied to the mobile phone output terminals. Now, a charger must maintain a constant output voltage even when the load changes. This function is handled by the feedback network consisting of 4N35 optocoupler 5V Zener diode, 100 ohm resistor, 470 ohm resistor. The optocoupler is a very important component because it transfers feedback information from the isolated secondary side to the primary side without any direct electrical connection. When the output voltage is below the desired value, the 5V Zener diode remains off. As a result, very little current flows through the LED inside the 4N35 optocoupler. The TNY267 therefore continues operating normally and delivers more power to the output. Now suppose the output voltage starts increasing. Once the voltage exceeds the Zener threshold, the 5V Zener begins conducting. This causes current to flow through the optocoupler LED. The light from the LED activates the internal phototransistor of the 4N35. The phototransistor then sends a feedback signal to the TNY267. The TNY267 responds by reducing its switching duty cycle. As a result, less energy is transferred through the transformer and the output voltage falls back to the correct value. This continuous adjustment keeps the output voltage regulated. Without an optocoupler, it would be difficult to send feedback information across the isolation barrier. The optocoupler solves this problem using light. The LED and phototransistor are optically coupled but electrically isolated. This allows safe voltage regulation while maintaining complete isolation between the primary and secondary sides. So that's it, friends. If you are interested to build a 220V mobile charger quickly and safely, you can try this concept. Thanks for watching.